the conference. So that will be the talk that merges the two submissions. So it will be longer. And the speakers are Sarah Lee and Xiaoning Bian from Dalhousie University. So please, the floor is yours.
Thank you. Just to test my volume, is it good enough? Can you hear me?
Yes, yes, I think it's
okay. Okay, awesome. Well, thank you, Dr. Hordetsky, and we would like to thank the organizers for this amazing opportunity. Thank you so much for your time and efforts. So today we're going to tell you about the generators and relations for two interesting groups in quantum computation. So we start by defining Z1/2 as a ring of dyadic fractions whose denominator is a power of 2. We define ONZ1/2 as the group of orthogonal matrices over this ring, and we call it the group of orthogonal dyadic matrices. It consists of n-dimensional matrices of this form, which is just a kth power of 1/2 multiplied by an integral matrix. For example, U is a group element in O5 Z1/2, and if you multiply the scalar 1/2 squared to every component, you'll see that the group, like the matrix, is actually composed of dyadic fractions. Here, U is orthogonal. In linear algebra, an orthogonal matrix is a real square matrix whose conjugate is equal to whose transpose is equal to its inverse. And one of its important property is that any two rows or columns are orthonormal. And this will allow us to investigate this group from a number theoretic perspective and define an exact synthesis algorithm. And then we adjoin a complex number I to the ring of dyadic fractions to get Z1/2 I. It is composed of element of the form R plus Si, where R and I are just dyadic fractions. And note that here, this is a subring of the complex numbers. We then define UN Z1/2 I as the group of unitary matrices over this ring, and it consists of n-dimensional matrices of a similar form as before. So it's a scalar multiplication between a kth power of 1/2 and a matrix of Gaussian integer. And a Gaussian integer is just of the form x plus yi, where x and y are integers. So for example, let's say n is a 3x3 matrix of this group. And then if you multiply the element, the scalar, into every component, you'll see that this matrix is composed of elements from this ring. And this matrix is unitary. And as a recap of linear algebra, a unitary matrix is the matrix whose conjugate transpose is equal to its inverse. And actually, its real analog is orthogonal matrices. And it is easy to show that the group UN Z1/2 I contained the group of orthogonal dyadic matrices. In fact, there is a correspondence between families of quantum circuits and group of matrices. In 2020, Amy, Glaudell, and Ross show that a circuit over naught, C0 Toffoli, and a tensor product of Hadamard gates can be exactly represented by an orthogonal dyadic matrix. And a circuit over naught, C0 Toffoli, a scaled Hadamard gate, and a phase gate can be exactly represented by a matrix from this group. This means that in order to study quantum circuits, we can now study the matrix groups. And here we call the circuits over this generating set as restricted Clifford plus T circuits. Well, we know that the restricted Clifford plus T circuits are they are well suited for fault-tolerant quantum computation, and they're universal. So we are very interested in this group. So now, in our study, we're interested in the constructive membership problem. So consider G to be a group of matrices over some ring, and we know that it is generated by a sequence of elements S1 to SQ. We also call them as generators for this group. Now, if you give me an arbitrary group element, how can I find the exact representation of this element over this generating set? And here, the dot product just means matrix multiplication, and the L here registers the length of the decomposition. And you can see that the smaller the L, the shorter the decomposition and the better the solution. And we consider a solution to be optimal when the sequence gives us a shortest possible sequence. And know that here, the solution, the optimal solution may not be unique, so we can have multiple variations of it. And in quantum computation, the exact synthesis algorithm provides a solution to the constructive membership problem. Now, as we have shown, restricted Clifford plus T circuits play an important role in many quantum algorithms, so we are very interested in these groups. In order to find a good solution to the constructive membership problem, we hope to design an effective exact synthesis algorithm. And to that end, we first represent our groups in terms of generators and relations. And since the technique to study both groups, the ONZ1/2 and UNZ1/2I, are quite similar. So in this talk, we mainly focus on the group of orthogonal dyadic matrices. So now let me tell you about some of the basic matrices in this group. Firstly, we have this X gate. It is just a 2x2 matrix, and it is acting as the NOT gate when it is acting on a vector. So it will just flip the two elements. And here we have this -1 gate, and it will later used as a scalar matrix. And we call the H gate as a Hadamard gate, and the K is just a tensor product of the Hadamard gate with itself. So it's just a dimension 4 matrix. In the other group, the larger group, we also have the NOT gate, but here we have this I. It is just a complex number, a 1x1 dimension matrix. And here we call this omega dagger H as a scaled Hadamard gate, where omega is just the 8th root of unity. Okay, so now let me tell you what roles these matrices are going to play in defining the exact synthesis algorithm. Basically, we're using them as a prototype to define an Nlevel operators. For example, let's say we're defining U alpha beta using a 2x2 matrix U. So what we're doing is when this matrix is acting on a vector, it will act exactly like U on the alpha and beta element, and it will act trivially on every other element. For example, let's say we have a NOT gate. And if we're defining X to 4 in the context of a 4x4 identity matrix, then we are just embedding this matrix into corresponding position so that when it is acting on a 4-element vector, it will just swap the first and the fourth element, but it will not touch the first and third elements. So you can see that our 2-level operators act locally on a vector. Similarly, we can create a 4-level operator by embedding a 4x4 matrix U into an n by n identity matrix. For example, let's say we have a K gate, and defining K1, 2, 4, 5 in the context of a 5x5 identity matrix will give us this extended form, so that when it is acting on a 5-element vector, it will perform linear transformation as instructed by the K gate, but it will not touch the third element. So in our research, we define a generating set G. It is composed of 1-level -1 gate, 2-level NOT gate, and 4-level K gate. And here, this -1 alpha is just acting as a scalar. When it is applied to the left of a matrix, it will flip the sign of the alpha row. And when it's applied to the right of a matrix, it will flip the sign of the alpha column. And actually, Amy, Glaudell, and Ross show that this set is indeed the generating set for the group. And this will become very handy for us to find the relations for our group. To establish this theorem, we need to do 2 directions. So for the first one is, since we know that all of these generators are in our group and the group is closed under multiplication, so that any product of elements of the group is indeed in the group. But for the other direction, we need to show that for any arbitrary group element, we can find a sequence of generators that will exactly represent this element. So this means that we need to define the synthesis algorithm. But in order for me to tell you how does that work, let's look at this little notation called the least denominator exponent. Consider dyadic fraction T, and it is of the form where the numerator is an integer and the denominator is a power of 2. Here, this exponent is just called the denominator exponent of this dyadic fraction. And since we know that we can always find a reduced form for our dyadic fraction, then the minimal such k is called the least denominator exponent. Or if you think of it the other way, it's when we can no longer factor out 2 from the numerator, then we'll find the smallest such k that will give us this value. For example, let's say we have a vector composed of 8 elements, and the LDE of this vector right now, well, we don't know yet, but the denominator exponent is 7. But since we can factor out 2 from every component of this integral part, we'll get a new form, and that will allow us to further reduce the denominator exponent from 7 to 6. And since now the integral part composed of odd entries, this means that we reach the reduced form, and that gives us the LDE of the vector. Similarly, we can define the LDE for our matrix, as you can see here. Following, there are 3 lemmas, and this actually summarizes some of the important properties of a vector composed of dyadic fractions. And by establishing these 3 lemmas, we're able to find out a column reduction for any input matrix into our algorithm. So let me show you how it works. In the base case, and that's when the LDE of a vector is being 0. Since we know that the vector has unit norm, by direct computation, we can show that it is a basis vector up to the sign. Now, consider a unit vector when it has positive LDE. Then we can show by direct computation that in the integral part of this dyadic fraction vector, the odd entries occur in quadruple. But how could that help us? Well, we further prove the parity reduction lemma, saying that given 4 odd entries, there exists a sequence of generators that will send these odd entries into even elements. And by using these 3 lemmas, we are now ready to define a column reduction. So let me illustrate it with an example. Let's say we have a vector composed of 8 elements, and this LDE is equal to 2. Then the column reduction lemma assign a sequence of generators, G1, so that they will act locally on the top 4 odd entries to send them to even. And then applying G2 locally to the bottom 4 odd entries, we'll get V double prime, where all of the entries in the integral part becomes even. By factoring out 2, we reduce the LDE strictly by 1. And by applying the same trick, we get V triple prime, where the LDE of this vector is 0. And that gives us the base case where we know that the vector right now is just a basis vector up to the sign. And this gives us the exact synthesis algorithm. In a nutshell, the algorithm works column by column. It always starts from the rightmost unfixed column and will send this column to the basis vector En, and then it will move on to the next column. It will send this one to En minus 1. So by iteratively reducing the columns to the corresponding basis vector, we were able to send this input M into the identity while outputting a sequence of generators at each step of reduction. And for those of you from computer science, this is just a process of reverse engineering. And now by concatenating the sequence of output from each reduction step, we're able to find a sequence of generators, G1 to GL, that will send our input matrix to an identity. And by taking the inverse of this sequence, we're able to find the decomposition of an arbitrary group element over our generating set. So now, with the generating set of our group, Bian will show you how to leverage the exact synthesis algorithm to find a complete set of syntactic relations for our group. Please take it away, Bian.
Thank you, sir. So let me share my screen. Here. Share. Yeah, so we have an exact synthesis algorithm for a group. So given a group elements, that algorithm output a sequence of generators. So basically, we want to exploit the algorithm to find the generator relations. So this method first appears in Seth gradient thesis, master thesis supervised by Peter Salinger in 2014, I think. So given that algorithm, we want to find a group presentation by generator and relation. So the generators and relation in our title actually means we have a group presentation. So by group presentation, we mean so given a group, given a generating set X J generated by the generators, and we can consider the X as symbols. We can consider X star, the finite sequences generators. Find a sequence of symbol. We also call it sequence of word. So we have a word, and so we can define a relation on word. So a relation just a pair of word, and we also write the relation as a W approx V. So that's a relation. To give a set of relations, we have many relations, maybe finite, maybe infinite, many relations on the word, and we can form the set of all the consequences. By that I mean this sim R means the smallest congruence relation containing R, meaning it's the smallest congruence relation. It's smallest equivalent relation. So it satisfies reflexivity, symmetry, and transitivity, and also the congruence rule. So we have two words. For example, if we have a word A and word B, and we know A is related to A prime, B is related to B prime, then A concatenate with B is related to A prime, B prime. Because in the X star, all the words, it's a monoid, so the operation, the multiplication after concatenation. So you put two words together, you get a new word. And so yeah, that's the congruence rule. So the smaller the congruence rule, we call that containing R. We call that R. That's smaller congruence rule, the consequence of R. So, and we can define sound. So given a set of relations, and we see R is sound if all the consequences are true. By true, I mean because right now all the words are sequences of generators, you can form the product. So we have a semantic for that word. Just send the sequence of generator to their product, to the group product here. So we have the semantic bracket. And so if the semantic is true, I mean, if two words are semantically equal, then we see the two words the relation are true. So this, I mean, so all the consequences of R are true consequences. So that's sound. All the consequences of R are true relations, are semantically equal. So that soundness and complete means all the semantically, so they represent the same group element, all semantically equal words, they actually are consequences of R. So our R actually capture all the semantically equal words in them. So if our relation is sound and complete, we will see our XR is a presentation of G of our group. So that's what we mean by generators and relations in our title. We want to find a sound and complete relation for our group. And so that's our main theorem. So this is a merge talk from two papers. So each gives a presentation for a particular group. So for example, Lee, Ross, and Sandra in this paper, they give the presentation for this orthogonal group. So the group Sarah just introduced. So introduced from this dyadic ring. And in this paper, Bian and Sandra, we give a presentation for the UN unitary dyadic with introduce the dyadic ring plus the I. So yeah, so basically, yeah, sorry, we have presentation. So we have sound and complete relation here. So one of the relation here. So that's for the orthogonal group. So we have several parts. The first part says something about the order of the generators. So for example, all the things have order 2 here, order 2. And this part says the generators with distinct indices actually commute. AB, CD becomes CD, AB, this group for a relation. Here says X gate can be used to change so if you move this X gate here, you can see this -1B becomes -1A, actually change the indices. So there's some, we can analyze the meaning of these relations, and there's also some actual stuff that's kind of particularly related to this particular group. And similarly here, for the relation for the other group, it's a little bit simpler because we only have 2-level operator. We don't have the 4-level thing. So things become simpler here. And we have similar parts of relation here. Order here, we have order 4, order 2, order 8, and something similar. So that's our presentation, that's our relation. So the main part, the actually, so all we need to show is the relation of sound and complete. You see all the relation are finite, so sounding is not a problem. We just verify finite many equations. That's trivial basically. So the only hard part is the completing the proof. So because the group kind of abstract, we need something to have a hand on to work on. So we need a graph, the KD graph for a group. So that's simple because the definition is simple. So given a group generated by a set of generators, we can construct a graph. All the graph have vertices, all the group element. If from a vertex X to vertex R, that for edit that edge, if we have a generator G times S equals R. So that's our KD graph, and because our exact sensitive algorithm could output a sequence of things, a sequence of generate reduce some element to the identity matrix. So actually, the exact sensitive algorithm actually gives a path from each element to the identity matrix. So we call it path a normal path. So every element have a normal path. So basically we have a spanning tree for this KD graph. The spanning tree comes from the algorithm. Everything that is unique path to identity. And so another thing in the algorithm, so we output a syllable at each loop. So we call that syllable. So basically, I mean, maybe 2 or 3 edges combined together. So we can generate combined together because each syllable reduces the LD or something. So we call that a normal edge. So now we have a KD graph with normal path with normal edge. So basically that's enough for us to work on using this terminology here. And so the hard part is the completing the proof. So so we use this lemma 1. Lemma 1 says every word is related to its normal form. So U is related to its normal form, its normal path. And so we'll show the lemma later. But the lemma 1 implies completeness because U is to show completeness, we have 2 words have the same semantics. Have a same semantic means have the same matrix. So you input the matrix in the exact sense algorithm, you get the same output. You get the same sequence here, same normal path here. So U is related to this normal path. V is related to normal path. So that implies U is related to V. So this implies this. So that means the completeness. So now the hard part transfer to this lemma 1. We want to show lemma 1. And so to do, we have to use the induction because there's every word. We have a length for every word. So we do induction on the length. For example, so right now we have n symbol here. We have a word of length n. We do induction. So assume we can show the commutativity of this triangle. So by commutativity, I mean this triangle is a consequence of R. So this equals this. It related to the other part. It's a consequence of R. So if we can show this triangle, then this R has length n-1. We can do induction on the rest. So the difficulty comes to show. So to show the triangle, and just 1 minute. Yeah. So here's the triangle. So we call So I just move this triangle to here. That's basically we need to show. For a normal path extended by an edge, it can be reduced. Can be related to another normal path by R, and so the way we do this is, maybe we can find some edge here connects this point to this point. So, and then do some induction. So that's the detailed induction step. So, if we can find sequence here from this point to this point, and maybe we can even make this triangle smaller. So this triangle becomes smaller because before there's a big triangle, now it's smaller. We can do induction on this smaller triangle. And if all the smaller triangle commutes and this square commutes, then we know the outer layer big triangle commute. So that's how we show this induction step. Normal edge extended by a single edge reduced to another normal edge, a normal path. So yeah, so then the difficulty comes to find a computational square. I mean, to show our R implies this square commute. So that's our main lemma. So just ignore all the sentences here. The main thing is we can always we want a complete square. So basically, we do some case distinction, or we want complete square. We just record what we need. Oh, I need this relation. So I put this relation in my relation. I record all the relations I needed. Then all the things, then I know my relation is complete. And one other thing, we need to make sure we indeed get smaller triangles. So that the actual things we want our level, the levels on this edge is smaller than this one. So basically make sure the triangle becomes smaller, so the induction goes through. So the proof for main lemma is by the finite case distinction, because yeah, we can make this finite only because we are working on these two particular groups. For other groups, we tried other groups, but we cannot make the casing to be finite. For example, you always have one case split into two cases, and subcase split another two cases, and the cases just keep increasing. So we are lucky to have to find a finite casing for this O1 and for the UN, and yeah, that's the particular group that make this happen. And yeah, for the future work, maybe we can improve the complexity of our exact sense algorithm. For the not column by column, maybe we can do 2 column by 2 column. This way we can reduce the length of a normal path. Of everything is more closer to the identity matrix. So the other thing, we can investigate the Clifford. So right now we investigate the restricted Clifford 2-level operator relation. Maybe you can investigate the circular relation. We did some work for the 2-qubit case. So the hard part is because in the circular thing, you have tensor I, tensor H, tensor H. You have this tensor as the building thing. But here in the 2-level setting, you kind of have the O plus I, O plus X equals 1, 1, X, X. So, but I tensor X is a different thing. Yeah, the things that's it's not so easy to do the translation. And also for a 2-level, if you want to express a 2-level operator in terms of circuit, it's quite complicated. So another thing, maybe find a minimal set for the relation. So right now we know the set is not minimal because we can derive one relation from the other, but we think the form right now we have is nicer, so we keep the redundant thing there. For the example, we keep the operator, the orders of the operator there explicit there because we want to know the order of the operators, the 2-level operator. And another last question, maybe we can investigate other Clifford restricted Clifford plus matrix group, such as maybe we put a root 2 there, not I root 2. Maybe put a I root 2 there. All these subgroups appeared in Matt's Ross and Glaudell paper. And maybe we can investigate that. And the largest group here, this is actually not restricted Clifford. This is the Clifford party. Second, the corresponding group for that group the 4 Clifford party circuit. And for this one, we did some work, but that's what I mentioned. We cannot find many things find many case dignity for this group. And yeah, that's all I have. And thank you.